Okay, in this lesson we're going to be learning about binary, and binary is the way computers speak, essentially. That's their language. And binary, as in bi, like bicycle, meaning two, means we have two different things. In this case, a 0 and a 1. In your brain of a computer, otherwise known as a CPU, it's basically full of millions of switches, and those switches only know on and off. So our 0 and 1 is essentially an on. Oop, I've done it around the wrong way here. This should be on and off, and that's why binary is the way computers talk, in zeros and ones. But we're used to talking in decimal and having all of the numbers 1 through to 10, and we came up with that because it enabled us to count on our fingers. However, in order for us to represent all of the other characters that we use, like letters, symbols, and also numbers, we need a way to represent those as zeros and ones so that the computer can process them. So the way we do that is we essentially initially use exponents, which I understand you're learning about in Year 7 Maths at the moment, to give ourselves a base set of numbers to work with. So at the moment I'm writing out a whole bunch of 2's with their exponents above. So 2 to the power of 0 is actually 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, and so on. 16, 32, and up to make up a whole byte, if you remember learning about bytes, we would have 8 of these. So at the moment I've got 1, 2, 3, 4, 5, 6, 7. We're going to go up to 128 here, which is 2 to the power of 7 is 128. So because I have 1, 2, 3, 4, 5, 6, 7, 8, it's big enough to make a byte. So you might remember in class I said if you've got a series of 1s and 0s, however that looks, you've got 8, that is a byte of data. 1 byte. Incidentally, sometimes, especially when we're learning to talk in binary, we just use the first 4, and a bit like biting an apple, the first 4's half as much, so we call that a nibble. We've got bytes and nibbles. Alright, so I'm going to go back a step here, and we're going to get rid of our byte, and we're going to start with the number 1. So to represent the number 1 as a nibble, it would look like that. That is 0001, and that equals 1. And the reason it equals 1 is because we have 1, 1, like that. Now to represent 3, we have to do something a bit different. We've got a 2 plus a 1 equals 3. So it's important to say here that that is not 11. That is part of 0011. And in computer speak, that is a 3. Alright, we'll do another one of those. If I've got a 1 here, and let's say I have a 1 there, 0, what do you think that equals? Well, I've got 1, 8, so I've got an 8 there, plus I've got a 2. 8 plus 2 equals 10. Alright, so we know what that one is now. I'm using my little erase thing, I probably shouldn't have bothered with that. It's a bit messier than hitting the undo button. But they are still just nibbles. If we want to go for a byte and we want to make a bigger number, we might have a couple of 1s there, 0, 0, 0, 1. That's a whole byte. So I'm going to have 128 plus 8 plus, that's meant to be a plus, let's try that again, plus 4 equals, so 12 is 140. 140. Just running out of space there with my menu. And that is how binary works. Now, when you're looking at your worksheets, the first one is actually talking about the decimal system. Remember, the decimal system is based on our finger counting. It's not what computers use. It's just to warm you up to what this all means. So to fill out the rest of this one, you're basically just doing each number. Just the important thing is when you get to 10, that you're using each spot there. All these blank ones are essentially zeros. So in decimal, 000 equals 0. 001 equals 1. 002 equals 2. And then when we get down here, 011 equals 11. And so on. So that's decimal. That's not computer speak. That's just sort of outlining the difference between that one and when we get over to binary here. With our binary, we've got 000 equals 0. They've left this area here. That's essentially going to be just about all zeros, I think. So really, we're working in nibbles. 0001 would equal 1. And then when we get down a bit further, they've given an example one in here. It's literally 1, 2, 3, 4, 5, but 0, 1, 1, 4. So you got 4 plus 1, 1. So you can have a 1 there. 4 plus 1 equals 5. And in their worked example, that's pretty much what they've done. 1, 4. We've got 0 2s, because 0 2s. And then we've got 1, 1 equals 5. So it's just a different way of sort of showing you how they're figuring it out. And then you have to go on like that throughout the whole table. These will all be zeros. Now the next one's going to be 6, so you have to work out what of these numbers can I use to add up to 6. Well, it's pretty obvious, isn't it? It's the 4 and the 2. And everything else will be zeros. That is how to do that one. This next one, students get a bit confused. This is actually multiple choice. Sorry about my writing with the computer pen. So one of these is the answer. And when it says the first 5 binary numbers, it's literally looking for 1, 2, 3, 4, 5. And to work these out, I'll give you an example. If we take that, there's only 3 numbers here, so this should be pretty easy. If you think of our 1, 2, 4, and the 8 I won't need. But that comes from the 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. The 8, 4, 2, 1 are the numbers I've got to choose from. And our number here is 1, 1, 0. So 4 plus 2 equals 6. That number there is a 6. Let's try this one. 1, 0, 1. 4 plus 1 equals 5. So that number there is a 5. And you keep going until you find A, B, C, or D that equals 1, 2, 3, 4, 5. The next one, these are all multiple choice, by the way. I might just show you this one because it's a bit longer. So question 3, what binary number comes after 110011? So to work that out, we've got to work out what number that is first. So again, using our system, 1, 2, 4, 8, 16, 32. Have I got enough? 1, 2, 3, 4, 5, 6. Yep, there's 6 numbers here. So we need 1, 1, 0, 0, 1, 1. 32 plus 16 is 48. Plus 2 is 50. Plus 1 is 51. All right, so what binary number comes after that? So we're looking for 52. And if I work out 52 here, I'm going to have a 32, 48. And you can work the rest of that out yourself to work out which one of these equals 52. Just one other one I'll touch on. Question 11 was fairly tricky, and I'll just give you a little clue. So remember, a bit is a 0 or a 1. That's a bit. And 8 bits make a byte, but you don't need to worry about that for this. It's saying, suppose binary numbers are used to represent each uppercase and lowercase letter plus 12 symbols for a total of 64 different characters. So a binary has to represent 64 different characters. In order to do that, just think about, well, if I've got just one bit, how many different characters can that represent? Well, 2, either a 1 or a 0. That's 2 different characters. The 0 could be an A and the 1 could be a hashtag. It doesn't matter. It's just about how many characters it can represent. If I have 2 zeros or 1s, now I can potentially have 1 1, 1 0, 0 1, 0 0. So that's 4 different characters. That's 2, 4. If I have another bit, it's going to be, you'll see a pattern here. I can have 1 1 1, 1 1 0, 1 0 0, 0 0 0, 0 1 1, 0 1 0, and then 0 0 1. What have I got now? 1 2 3 4 5 6 7. I'm sure it's 8. What am I missing? 0 0 0. So that 8 there. So I can represent 8 different characters with 3 bits. How many characters, how many bits do I need to represent the 84? And that should, oh no, I'll comment on this as well. If you get up to this, or when you get up to this, you don't need to cut it up. I know it says that, but you don't need to cut it up. Just use it as is. Use it with a friend, and Miss Tinny and I will be very impressed if you're able to answer the last bit here. So good luck with that. You will be able to play the game. I think you'll work that out okay. But the last bit is an interesting puzzle for you keen beans there. All right, good luck with that.